The following images will demonstrate the use of the QPF-PoP relationship combined with the neighborhood approach to PoP forecasting. I have conducted research on this topic at the National Weather Service in Goodland and continue to develop the approach with the Office Science and Operations Officer for operational deployment at the office. The first step to the approach is to pick a model to use that occurred in the past. Any model can be used for this approach. For this example, the Konzal model was used. This approach is based on the findings in the literature that a model quantitative precipitation forecast, or QPF, is usually erroneous in regards to the amount of precipitation that it forecasts to occur. However, models do a pretty good job at identifying areas where at least some precipitation is more likely to occur when they increase the QPF amount in areas compared to those areas that have little QPF. Taking a Konzal QPF field in this image, a neighborhood calculation is done by averaging the QPF amounts for a number of points around a grid point of interest, and then reassigning the average neighborhood QPF to the middle grid point of interest. Averaging the QPF amount from points around a central grid point accounts for model spatial errors and allows for a more accurate representation of a QPF. The number of neighborhood points is also recorded to determine the percentage of agreement among the points of precipitation that is forecast to occur, or for example, precipitation above 1/100th of an inch. After the neighborhood calculations are finished, each grid point in the domain is placed into a precipitation bin for every scenario of neighborhood agreement percentages for the different QPF amounts. For this approach, precipitation bins are used to verify the QPF that closely match those used by the National Centers for Environmental Prediction, or NCEP. Once an average QPF and the percentage of agreement are determined by the neighborhood approach for each point in a forecast domain in the Graphical Forecast Editor, or GFE, and then placed into a precipitation bin, we then use the Quantitative Precipitation Estimation, or QPE, from the River Forecast Center as the observed precipitation to verify how the forecast performed for each neighborhood agreement and for different precipitation ranges. The River Forecast Center QPE is shown here in this image. For each point across the domain and for each precipitation bin, the QPE checks to see if precipitation actually occurred at the forecast point that had something other than 0 for the QPF. Here is a conceptual model of what a neighborhood looks like when it is being computed in computer code. The black dot for the middle grid point represents a forecast point within a grid point of interest. In this example, one grid point in each direction is considered in the average QPF calculation in the north, south, east, west, and diagonal directions. Once an average QPF is found within the neighborhood, it is reassigned to the center point, and the number of points in the neighborhood that agree to having precipitation is also recorded. Numerous days and forecast hours are considered to generate PoP tables using the neighborhood approach based on past forecasts and observations. Let's demonstrate how the approach uses this table once it is generated. For example, let's pretend that a current forecast uses the neighborhood approach, and our point of interest has a QPF that falls in the 1/10 to 1/4 of an inch of precipitation bin and has 40% of the neighborhood points agreeing to have some sort of precipitation occurring. Therefore, based on past observations that were used to create this table, the probability of precipitation forecast would be almost 32%, because 32% of the time precipitation occurred within the past data when this same scenario presented itself. This entire process is done on numerous dates for different precipitation scenarios to help create PoP tables to use for forecasting. Once PoP tables are created, the PoP tables can be used to forecast future scenarios using different neighborhood sizes. Above is the forecast using the neighborhood approach for a small neighborhood based on the Consol QPF field. The small neighborhood size includes points around a central point that had a radius of 40 kilometers. So this is what the smaller neighborhood looks like when loaded into GFE. This image is a larger neighborhood PoP forecast that considers points using a search radius of 110 kilometers around a central grid point. This is what the large neighborhood PoP forecast looks like when loaded into GFE. This image is the Consol SmartInit PoP forecast that is currently in use by GFE and the National Weather Service. Both the smaller and larger neighborhood sizes and the PoP forecasts ended up verifying better using the Breyer score statistic as used in Boise Verify when compared to this regular PoP forecast shown here. Here is another example of how the neighborhood approach using precipitation binning can lead to more accurate and useful forecasts. The above is a GFE forecast that was based on the NAM12 SmartInit. And here is the NAM12 neighborhood PoP forecast that shows a more true probability compared to the sharper contrast of the previous image where the NAM SmartInit forecast was used for PoP forecasts. This approach leads to more useful and accurate forecast guidance to be used by the forecaster in the National Weather Service, both for the long and short-term forecast periods. The chart above shows how the neighborhood approach compared to the SmartInit forecast and the official forecast in terms of the Breyer score from the months of March through June 2014. The neighborhood approach performed better than the two other approaches most of the time between both the 0Z and the 12Z model runs. It is operationally feasible due to the short computer run times and requiring little computer resources to run on AWIPS workstations in the office. I believe this approach is a glimpse into the future of how PoP forecasting can be improved in our agency and how it can be used at National Weather Service offices nationwide. Thanks for watching and listening to this presentation.